Hello and welcome to this next lecture on fundamentals of acoustics. We are looking at solutions of wave equation using Fourier transforms for cases where initial conditions are present and maybe forces are present and variations of that. So, the next case we are going to look at is a forced response again of a fixed string that means homogeneous boundary conditions okay, and the force can be general and it has some initial conditions. And force can be general, force is some x comma t. Okay. The only assumption is this can be written as some other f of x and some g of t can be separated. Okay. So let us begin. So, we have the forced string equation del 2 w of x comma t by del x square plus f of x comma t over t is equal to 1 over c square del 2 by del t square w of x comma t, and string lies like this. Okay. And what are the boundary conditions? Let me just state it. The condition at x equal to 0 for all time t is 0, and the condition at x equal to L for all time t is also equal to 0. It is a fixed string. Okay. And what are the initial conditions? The w at x comma t equal to 0 is equal to w 0 of x, and del w by del t x comma t equal to 0 is equal to w dot of 0 of x. Okay. So, all of them are here. We have homogeneous boundary conditions, we have a general forcing, we have initial conditions, we have non-zero initial conditions. Okay. So, now we are going to use the Laplace transform. Okay. We will use the Laplace transform. So, we take the Laplace transform of this equation. Okay. If we take the Laplace transform, what do we get? We get del 2 w, I will use capital now, del x square of x comma s. Okay. That is the effect of the Laplace transform, plus the t variable has become s. Okay. And on the right I have 1 over c squared, and double derivative with time brings an s square, then I have capital W x comma s, then we have initial conditions s w 0 of x minus w dot 0 of x. So, you need to know or refresh your Laplace transforms. I am not going into the very basics of definition and how initial conditions are handled. Okay. You are expected to know lumped vibrations for this course. So, so this is how the Laplace transform behaves. Initial conditions also come into the picture. Okay. So now what we are going to do is, let us take this del 2 w of x comma s del x square, okay, and I am going to subject it to a Fourier series calculation. Sine n pi x by L dx. Okay. So this is the first function, this is the second function. So if I do that, I have del w of x comma s by del x into sine n pi x by L over 0 to L minus an integral which has the integral of the first function and the derivative of the second function n pi by L cos n pi x by L dx. Okay. Now sine n pi x by L is our mode shape again, because why? Because fixed string we have seen just the last class. So this term goes to 0. Okay, this is 0 at x equal to L and x equal to 0. So I am left with this, and I will keep the minus here. Then again I apply the product rule. So what I get is w of x comma s n pi by L cos n pi x by L over 0 to L. Okay. Again minus an integral which goes from 0 to L w of x comma s, then n pi by L whole squared sine n pi x by L into minus 1 into dx. Okay. Now this w function, okay, this displacement function is 0 at L x equal to 0 and x equal to L. Okay. So then this term goes off and I have a triple minus over here. So I end up with minus n pi by L whole squared integral 0 to L w of x comma s sine n pi x by L dx. Okay, that is the effect of applying the transform on this. Okay, now this term we will call it w p n comma s. Okay, so let me see, let me take this to the next page. Copy, paste. Okay, so what has happened, let me recall, is that this is minus n pi by L whole square w p n s. Okay, minus n pi by L whole squared. W of p n comma s. So this I will write is p n, okay, minus p n squared. P n, let us remember, is n pi by L. Then I do the same thing, so this goes into a transform plus f p n comma s by t, okay. Then I have x all over the place over here, so they will go through the same thing. So that is equal to 1 over c squared, okay, let me put it, let me keep it here, 1 over c squared into s squared w of p n comma s minus n s w 0 of p n minus w dot 0 p n, okay. So we multiply by c square, so I get minus p n square c square w p n s plus c square by t f p n comma s, okay, that is equal to s square w p n comma s, okay, minus s w 0 of p n minus w dot 0 of p n, okay. So now I will bring this and this to the right. So what I get is s square plus p n square c square into w p n comma s minus c square by t f of p n comma s is equal to, I take this to the other side, so s w, I will keep it small here, w 0 of p n plus w dot 0 of p n. Okay, so now what happens? Now we have w p n comma s is equal to c square by t, okay, and then I said I am going to assume that this is separable. So I will again write it as sum f star, which is f again, okay, or let me keep it as f star p n and g of s by s square plus p n square c square, okay, plus s over s square plus p n square c square w 0 of p n plus w dot 0 p n by s square plus p n square c square. Now just to remind ourselves, if we have a over s square plus a square, inverse of that is sine a t, Laplace inverse, and if we have s over s square plus a square, the Laplace inverse is cos 8. Okay, just to, we are going to need it, that's why. Okay, so now what we have is that when we try to get back to the space w of x comma s, this is small w, is now 2 over L summation w of p n comma s sine n pi x by L. Okay, just as before. Okay, so now we supply w p n comma s here. So w of x comma s is, let's say, 2 over L, okay, summation c square by t f star of p n g of s by s square plus p n square c square, okay, that's one term, plus 2, okay, into sine n pi x by L, then 2 over L summation, the second term, s over s square plus p n square c square w 0 of p n plus w dot 0 of p n by s square plus p n square c square. Okay. So now what do? What we do is that this here is adequate, this will form a cosine type inverse, but this here is inadequate because it requires a p and c on the top. So what we will do is we will multiply by p and c, divide by p and c. p n is this, if you recall. Okay. So now if we bring back everything into space, so what I have here is 2 by L summation n from 1 to infinity, okay, c square by t, then fp is now integral 0 to L f of xi sine of n pi xi by L d xi, okay, into sine n pi x by L into g of s by s square plus p n square c square. Okay. Now here also I have the same problem, so I will multiply this by p n c, okay, and divide by p n c. Okay. So let me do one more thing, I just want to confuse. So let's get this a little to the right, then plus comes here, and then I'll do 2 by L summation. n equal to 1 to infinity. So keep it separate, just keeping it separate. Okay. So this is one level that is equal to this. Then I have plus 2 over L summation n going from 1 to infinity. Okay. S over s square plus p square n c square w0 pn is integral 0 to L w0 of xi sine n pi xi by L d xi. Okay. One more thing I missed. Let's do that also. Okay. So here okay, so have a sine n pi x by L, and here also have sine n pi x by L. Okay. So here I have an extra sine n pi x by L. Okay. In the last one I have 2 over L summation, okay, 1 over p n into c p n into c by s square plus p square n c square integral 0 to L w dot 0 of xi sine n pi xi over L d xi, and again if I enclose it sine n pi x by L. Okay. So this is what w of x comma s. Okay, w of x comma s. It's big, it's a big w of x comma s. So that I want this on the next page. So let's go. Okay, this is w of x comma s. Okay, so now we have to invert the time, okay, as the final step of the Laplace transform. Okay. So what do we get? So we get here we get now w of x comma t, okay, is let's see what we have. So we had a P and C, we had a P and C and a P and C for this also. So we have a P and C and a P and C here also. Okay. So we have now is equal to, let us see, summation over n equal to 1 to infinity 2 by L rho L C square, which is the T. Okay. Pn is n pi by L into C and C square. Okay. So what happens? This goes with this goes with this. Okay. And I finally have 2 by rho L n pi C. Let me do that. 2 by rho L n pi C. Okay. Then I have this integral 0 to L f of xi sine n pi xi by L d xi into sine n pi x by L. Okay. And this, the last term ends up looking like integral 0 to t g of t minus tau sine n pi c tau by L d tau. Okay, that is this term. Okay. Then plus, okay, plus, let us see, summation, I take this in 2 by L. Okay. The Laplace inverse of that is a cosine. Okay. Laplace inverse of this entity is a cosine. So what is that? It is a cos n pi c t by L. Okay. And then we have this integral which is 0 to L w 0 of xi sine n pi xi by L d xi into a sine n pi x by L. Okay. And then we have plus a summation n equal to 1 to infinity, I should keep doing that, 2 by L n pi by L c. Okay. Then this term is sine n pi c t by L, this term. Then okay, a sine n pi x by L, that is this term, and then integral 0 to L w dot 0 of xi sine n pi xi by L d xi. Okay. So we have this goes, is 2 by n pi c. Okay. So this is the first term, this is forcing, these are the two initial conditions. Okay. So that is how you deal with fixed string, homogeneous boundary conditions, a general force using Laplace and Fourier, and then initial conditions. Okay. I will close the lecture here. Thank you.